Hello, I'm Mike McCulloch. Today I'd like to talk to you about capacitor thrusters. So this all began just after I'd written a paper on M drives and dielectrics. So the M drive, as I've discussed in a previous video, is a metal conical cavity full of microwaves resonating within it, which seemed to show a thrust towards its narrow end. And this was invented by Scheuer, and I found that when I applied quantized inertia to these M drives, I could predict the thrust that Scheuer and some others as well were seeing. Furthermore, and I published a paper on this M drives and dielectrics, I found that when a dielectric was put within the M drive, it changed the thrust, and I could predict that as well very accurately. And as I said, I've discussed this in a previous video. But then I received an email from Frank Becker, who's an engineer in California, and he said that he'd read my paper, and it had reminded him of some experiments he did years ago looking into the T.T. Brown effect, which is an effect discovered by Thomas Townsend Brown in the 1920s, wherein charged capacitors thrust towards their anodes, and Frank Becker had done some work trying to reproduce that, and he had some success with that, but he wondered if quantized inertia would predict it. So I started looking at capacitors, and I found that yes, indeed, quantized inertia does predict it, does predict the thrust, and I'll show you how in a minute. And Frank Becker also in parallel started to do experiments to see whether he could reproduce the T.T. Brown thrust, and he did experimentally reproduce it. Okay, so my derivation started from the Casimir effect. So what my intuition tells me is that this is a variant of the Casimir effect. So in that effect you have two conducting plates, and it has been shown and measured, predicted by Hendrik Casimir and measured by Alan Aspect, that these two plates, if they're very close together, they damp the quantum vacuum between them, so forcing them to move together. So it's a force pushing them together. So I thought, could this be related? And I think it is. So imagine you have two plates, and I'll put a schematic up here a bit later showing them, and then you have electrons jumping from the cathode, where there are more electrons, over to the anode at incredible speeds, so that the acceleration is so much that the underwaves are short enough to start interacting with the metal of the plates. Now normally, so the underwaves normally would see underwaves, but for normal acceleration it would be light years long. But if the acceleration is about 10 to the 19 or something like that, the underwaves shrink so that they can be short enough to interact with the metal. So yeah, long electromagnetic waves, at least electromagnetic waves, pass through metal, but short ones can't. So for very highly accelerated electrons, they would see underwaves that are damped between the plates. So showing this on the schematic, you have two plates, the dielectric, and for a normal electron acceleration you would have no problem, but for very high accelerated electrons you would have a void. The underwaves would be damped between the plates, and I've tried to show this on the plot by turning it from a bright colour into a blue colour, representing a cold area of underwaves, fewer underwaves if you like. This means that there will be more underwaves behind the electrons as they come off the cathode than there will be in front of them, so they'll be pushed forwards more than we expect. So there'll be an extra push on the capacitor, and the whole thing will move towards the anode, as indeed it does. So can this be theoretically predicted? Yes, it can. So you start from the Casimir effect formula. So F is pi C pi, H bar, so pi squared C H bar A, where A is the area, over 240 d squared, where d is the separation between the plates. And then what I did in the derivation was that I considered H bar. Now normally this is the energy time in the quantum background, but in this system we're putting in a lot of energy and a lot of electricity, if you like. So I changed H bar in a way that's still dimensionally correct, but it represents this extra energy that we're putting in. So it's the units of H bar are joule seconds, so we have an energy and a time. So the energy is obviously the energy we're putting in, and the time is the time that it stays within the cavity. So that is some representation of H bar in the formula. And if you work this out, you get Pd squared over V squared. So P is the power you put in, D is the separation of the plates, and V is the speed of the electrons as they go across. The speed is given by this formula, QeV over ME to ME. And also power can be represented as current times voltage. So if you put all these in, you get this formula. So the force you expect, the extra force you expect on the electrons is going to be 0.00014 times the current times the area divided by the separation of the plate squared. And I should note here that the equation, the constant here is not just a constant. It's formed of parameters like the charge on the electron and the mass on the electron. Okay, so this is a prediction of quantized inertia for the thrust you get from the capacitor, and this is a graph showing what was observed, the prediction with what was observed. So on the x-axis we have the separation between the plates, so about 100 micron on the right hand side going down to about 10 micron on the left hand side, and the force observed is shown up the y-axis. And you can see that as the separation between the plates was reduced, the thrust went up exponentially, and that's expected from this formula. The predictions of the formula, the data is shown by the solid curve, and the prediction is shown by the other curve. And the observation is shown by the black, and the prediction is shown by the open symbols. And you can see that the prediction is perfectly in sync with the data here. So quantized inertia predicts these capacitor thrusters really well. It predicted the results from Becker and Batt's test in California, which is the one showed here, and it also predicts very well other tests that have been done by the American company Ivo, by a lab I set up with Richard Arundel here in Plymouth, and by other labs in Italy and other places as well. So the maximum thrust seen by Becker and Batt in this case was about 6 millinewtons, which is still small, but the great thing here, and what the theory predicts, is that this can be hugely enhanced. If you just shrink the distance between the plates, then you can enhance the thrust massively. And this should be possible, but what is important here also is that you get the electrons to tunnel across the gap. In order to have this fantastic acceleration, you have to get Fowler-Nordheim tunneling. So that's important as well. And that's why in these experiments you have to get the potential difference between the plates, and that is forcing the electrons across. You have to get that up towards the breakdown in the dielectric you put between the plates. So that's quite a tricky thing to do, because it causes explosions if you go too high, which we saw quite a lot in our lab, for example. But even at this stage, this thrust is about 300 times better than the thrust per watt you get from an ion drive. The ion drives are used on satellites, so this would be a significant advance. The only problem so far is that the thrust, although it's there most of the time, is still intermittent. and this is a problem. The main problem is because of the dielectrics that have generally been used, which is capped on between the two metal plates, which tends to burn out. So a better material would be very welcome here. Okay, so if we can get this thruster working repeatedly and consistently, then it revolutionises space travel. And so it could be that we've been handed the galaxy on a pair of capacitor plates. Okay, so I hope you've enjoyed this talk, and many thanks to my Patreon supporters. Please do join at Patreon. It keeps me going, and I look forward to talking to you next time. Goodbye.